Alright, here we go. Thermodynamics 1, Part 2. So it's going to be numbers 15 to the end. I think it's 27 questions. So we are on 15. Alright, an ideal monatomic gas is compressed. Alright, so that's work done on it, while its temperature is held constant. What happens to the internal energy of the gas in this process? Oh! Classic trick question. Classic trick question. Sort of trick question. I don't care what this says. Well, no, I don't care what this says. I do care what this says. If they're asking me about the internal energy, and they tell me the temperature is held constant, end of story. End of story. Because internal energy is linked to when you think of internal energy, you should probably think if temperature is constant, internal energy has to be the same. As long as you're not adding more gas or whatever to it, So what you want to remember is isothermic processes, constant temperature processes. Internal energy, the change in internal energy is zero. And while we're at it, I know it's not specifically related to this question, but if a process is constant volume, then the work done has to be zero. Because if you can't change your volume, you can't do any distance, right? Move the piston, right? Then work's going to be zero. And adiabatic processes, those are ones where there's no heat in or out. So Q is zero. Alright? So those are important things to keep in mind. In this case, it does not change because the internal energy of the gas depends only on temperature. There we go. That's our guy. Alright. 16. Just double check, make sure I didn't mess that one up. That was 15. Shit, yeah, okay. 16. An insulated container with a divider in the middle contains two separated gases. Gas 1 is initially at a higher temperature than gas 2. The divider is then removed. Which of the following observations might be made over a period of time as the two gases mix together, and why? Alright. This is one of those where we're going to have to plow through the answers. So gas 1 remains at a higher temperature than gas 2. Gas 2 because gas 1 Gas 1 remains at a higher temperature. On average, the molecules of gas 1 lose all of their kinetic energy to the molecules of gas 2 through collisions, resulting in gas. Don't like any of those. On average, the molecules of gas 1 lose some of their kinetic energy to the molecules of gas 2 through collisions, resulting in the two gases eventually having the same temperature. So here's the thing. They've got to come to the same temperature eventually. You did calorimetry in chemistry, right? They're going to come to the same temperature. And so really this is, every other answer says they somehow, how do you know, once they mix, it's different temperature like there than it is there, because they're all over. No, got to be D. 17. A monatomic ideal gas is initially at state A. Shown in the PV diagram above, the gas undergoes a transition from state A by the three different processes shown, where process 3 is isothermal. So all along here you have the same internal energy. So going from here to here is not a change in internal energy, because that's on an isotherm. This is constant pressure. This is constant volume. No work being done here, right? Alright. So let's see. Energy is added to the gas by heating in which of the processes? Well, Energy is added to the gas through heating. So I don't buy one, and here's why. This would indicate from here to here a decrease in volume. Something is pushing down on that piston at the top. That's energy in. If you also add heat, then you should go to a higher internal energy. But this is definitely lower internal energy. Remember, higher internal energies are out this way. So this curve here would be a certain internal energy. Everything back here has a less internal energy. Alright, so I'm ruling out, and ain't gonna be one. Alright. Let's look at this. So, strangely enough, it could be 3, I think. Hear me out. I know that the temperature doesn't change, but the volume did. Oh, wait a second. That means work was done by the gas. So in delta U equals Q plus work, you would have negative work for this situation because the volume increased and the gas did the work, so it would be negative. But you can't change internal energy because it's on an isotherm. So you have to add work to keep the change 0. So you have to add, did I say work? I have to add heat. So definitely 3. Check. Now we go look at 2. Well, here, we don't change the volume, so there's no work done. So this is not existent for this process. And the internal energy definitely decreases, so that would be heat removed. So it can't be that one. So I'm thinking it's just 3. I'll double check. This is number 17. Yep, I'm still firing on all cylinders here. Of course, this is only the second video of like 50 that I got to do, so this ought to be interesting. By the time I'm done AP1, I'll be blithering idiot, more so than normal. All right, 18. 18. Here we go. Oh, same crap. I threw away my paper with the diagram. Hold on. I get it. Okay, same diagram. Same diagram. Positive work is done. Okay, so first of all, no work here, correct? Vertical line, no work. Now, according to, focus this here. There we go. According to AP, positive work is done when the volume is compressed, when something does work on the gas. So in which one of these, 3 or 1, are we moving to the left? Are we compressing the volume? It'll be this one. So what you want to keep in mind is for AP, if the volume increases, that's negative work because the gas had to give up energy to do it. If the volume decreases, that's actually positive work. And so for this one, positive work is only done in number 1. All right, now I think I can give it a this. 19. A gas is taken from state I to F along a 2-step process. Boop, boop. All right. How much work is done on the gas during the process described? Find that area, you're going to have the right answer. All right, the area under there. And it is work done on the gas because it's going to the left. So it should be positive work done on the gas because just like we talked about in the last problem, if the volume decreases, that's positive work because something put energy into the gas. So I just need the area of this. This is 2 by 1,000. So that would be 2,000 pascals. Volume, so yeah, so it should be 2,000 joules. 19. Just making sure I'm getting these right, because, yep, I'm still good. All right, so just the area under there. All right, number 20. Sample of an ideal gas taken through the cycle above, the PV diagram. So remember, the area inside here, if it comes up, is the net work done by the gas, or on the gas, depending on how we'll look at it and see. All right, so if 1,000 joules of heat is added to the gas during process AB, that makes sense, because the only way you're going to raise its internal energy, if you're not going to change the volumes, that means no work, is by Qn. What is the change in internal energy of the gas for AB? Well, change in internal energy is Q plus work done. But AB is a constant volume process, so there's no work done. So the change should be, you're adding 1,000 joules, it should just be 1,000 joules. Yeah, okay. Check. Now, 21 uses the same diagram. In a certain, I think it's the same diagram. We'll see. In a certain process, 400 joules of heat is added to a system. Maybe not. I thought they would, but okay. So maybe not. Make sure you can see this question. So, take 2. This is number 21. Okay. In a certain process, 400 joules of heat is added to a system, and the system simultaneously does 100 joules of work. Come on. We got this, right? Q. So, heat's added. That's plus 400. The system does that much work, so that would be minus 100. Lost my pencil. And so the change in internal energy I would have is 300. It still increases by 300. I would say this. That's number 21, and I'm still correct. All right, 22. In the PV diagram above, the initial state of the gas is shown at point X. Which of the curves represents a process in which no work is done on or by the gas? You got this. You got this. It's the only one that doesn't technically have an area underneath of it. It's got to be this. It's got to be the one that goes from X to B. Very hot gas composed of equal numbers of positive and negative ions. Uh-oh, charge. Thermally insulated container and is in a thermal equilibrium at a temperature T0. The figure above represents the initial distribution of the ions. A strong, uniform electric field. When the heck did we take a left turn and end up in electricity? I knew I missed that turn at Albuquerque. Google that phrase, you'll see Bugs Bunny. It's for those of us that are old. Anyway, I knew I should have taken a left at Albuquerque. All right, so a strong uniform electric field is directed towards the bottom of the page, is now created in and around the container, and the gas is allowed to reach a new thermal equilibrium at temperature T1. All right. The electric field is now turned off and the gas is allowed to reach a final equilibrium temperature T2. How does T2 compare to T1? Good question. If I'm likely to mess one up, I've seen this question before and I'm still probably going to mess it up, but let's see. Let's see what one can do. So, here's my thought. T1 has got to be larger than T0. Because when you put that field on there, all these things feel a force and over a distance. The negatives are, let's see, electric field is pointed which way? So field's downward. So all the negatives are pushed this way by a force over a distance, whatever distance, it varies depending on the particle. All the positives are pushed this way. So there's a lot of F times D's going on there, and that's energy in. Like, work is being done by the electric field. So I'm guessing that work in would have to show up, T1 would have to be larger. Now the question is, they say, though, they turn off the electric field, and the gas is allowed to reach equilibrium temperature T2. And it's thermally insulated, so they're not losing anything to the environment. See, I'm wondering, okay, so once you've done that work, if it can't, so if I have delta U equals Q work done, this isn't a possibility. It's thermally insulated. And they're not heating it or cooling it. Initially, they do work on it, but it's what makes this question interesting, because it's not by compressing the thing. They actually do work with the whole electric field bit, which is, okay, that's what makes this an interesting question. But after they turn it off, there's nothing pushes them back or anything, so there's no more work being added in, but there's no heat going out either. I would say, let's see, T2 is less because the electric potential energy, okay, there is, all right, so there is that potential energy between them. Good, I didn't think about that. Added by the field, you know what, okay, so you did work in, but now there's force distance the other way. See, okay, so you've separated, here's my thought. You've separated them so that the positives are down here and the negatives are up here mostly, right? Okay. Well, and to do that, you had to do work because the field had to push them apart, force times distance. Now, you turn the field off, there's work again because they do work on each other. They pull towards each other, right? And so this will experience a force towards this, and this will experience a force this way. And it'll be positive work on this and positive work on this. So it's more energy in. So, because it's stored in the field. I did not think about that. So, I would say the final temperature would be more than T1 even. Kind of like shaking it back and forth. You get a shake one way would add heat, and so would the shake back. It's not like you remove that heat. So I would say T2 is more because work is done on the ions in the process of turning off the field. T2 is greater because the electric potential energy of the 7 is converted into, I would go with this. I would go with that. 23. Did I get it right? Yes. Yes. But I'm glad they said that whole thing about the potential energy. I did not think about that. So when they said that, then it makes sense. All right. There you go. That one almost got me. 24. Sample of gas in sealed container. This is temperature and pressure. Okay. Whose volume is held fixed. Okay, volume fixed. Pressure of the gas is measured, and the absolute temperature is as its absolute temperature is increased. Well, that must mean heating it, because if your volume's fixed. Graph of pressure measurements as the function of temperature shown above. According to the ideal gas law, which of the following is expected if the sealed container's volume is increased to 3 times the original value and the experiment is repeated? So they're going to increase it, but it's still going to be fixed for that other experiment. So what we want to look at is this. PV equals nRT. P is our Y. Right? So let's not solve that. P is going to be equal to nRT over V. Now what I want you to do is we want temperature to be our X. So everything else is going to be a constant because they hold the volume constant. All right, so we really have this as a linear thing would be P equals NR over V. That's our constant. T is our X. This is your slope, right? This is your slope. And then, as expected, if the sealed container's volume is increased, so I'm assuming it's the same amount of gas. And so by increasing this, the volume, you would decrease the slope. So I would expect a line, but I would expect it more like this. Would it go to the origin as temperature? Yeah, technically, as temperature goes to zero, there'd be no pressure. I would think A would be the right answer on first look, and I would be correct. Graph would show a linear relationship with the same slope. No, it wouldn't change the origin. There's no plus B here, right? There's no y-intercept in this equation. It's just y equals mx. So the y-intercept, yeah. So it's definitely a change in slope. This changes when you triple the volume. It makes the slope go down. So it's going to be A. 25, something we haven't seen usually in a while. So 25. The old distribution of speeds. Two samples of the same type of gas molecules are placed in different closed containers and are thermally insulated from each other in the environment. The figure above shows the distribution of speeds for the molecules in each sample. The two samples are now mixed together and allowed to reach thermal equilibrium. Which of the following is true of the peak of the distribution for the mixed sample? Okay, so this is at a cooler temperature because the average speed of the molecules is less. This is at a higher temperature, this substance here. We know that they're going to mix and form and mix and create and be at a temperature and equilibrium somewhere between these two. Same type of gas molecules. I don't know if it's the same number, but if it's the same amount of gas. But I would say it's going to be, let's see. So the question is it closer to 400? And so it's somewhere in here, right? The peak is going to be somewhere in here. Is it closer to 800? Is it exactly between? There's no. This definitely not D. Definitely not D. There are not two peaks. So this one of the answers here down here is there are two peaks? There are not two. No, they will come together and form one single distribution. Here's my thought. There's not a lot of gas. So the area under here is really the number of molecules. And it would be the area in, ready? So we would take this red right here, all right, and add it on there. So it would be, so the total area under there would look something like this. It would be there, so I'll do that in gray. So this represents the total number of molecules, some of it from the first substance, some of it from the second, and this would be their total, the area underneath, which would be the total number of molecules. How does that compare to the total number of molecules below 800, or even, look at, like, so I'm leaning towards that the temperature would be, the final peak will be a little bit to the left of the 600. Here's the other reason I'm thinking that, is even if the temperature ended up being halfway between, even if it was the same amount of gas and the temp ended up halfway, temp is average kinetic energy. Speed, there'd be a square root involved. Would be squaring involved, so you wouldn't need as much velocity to create that. So that's another reason why because you would be squaring it. It's another reason I'm leaning toward somewhere between 4 and 600. Now I could be wrong. I haven't looked at the answer yet, but I'm going with A. If I was a betting person, I would go with A. Now I'm going to cross my fingers and look at the answer to 25, and yes, baby. I kind of like my the final temperature is going to be the average kinetic energy. Well, Boltzmann's constant T. Even if that was halfway in temperature between them, it wouldn't be halfway in terms of the speed, because kinetic energy is 1/2 mv squared. And to produce that new temperature, you wouldn't need to double the velocity to get double the temperature, for example. Not that we're doubling it, but you get the idea. All right, almost got me. 26. Graph above shows pressure as a function of volume. So back to a PV diagram, illustrates a thermodynamic process for an ideal gas engine. Which of the following best describes the change in internal energy of the gas and the work done in the process? Well, let's do a little estimation here. I mean, it looks like it could be an isotherm, could be an adiabat. I don't know. We're going to find out, because in order to find the change in internal energy, they give me numbers. Yay. So this would be, in a quick thumbnail here, this would be 100 times 2.75. Yeah, I know there's all kinds of, 10 to the 5th, whatever. Just getting a feel for things. This would be 200 times 1. Well, I got that. That's 200. And since this is just 100 times that, that would be 275. So we go from 275. Once again, these are not official numbers. It would be, the unit, 10 to the whatever, to 200. That's a drop. Okay, so we lost internal energy. Okay, so it's one of these two. Now, this is a bit of an unfair question. A bit of an unfair question, a little bit frustrating for me. Yeah, here's why. So you would all say that the volume increased. And if you've been watching these earlier things, then I explicitly told you that's negative work. Well, in terms of delta U, Q, plus work, that's what I mean. That if you use this equation, AP would say that's negative work. No problem. But when they say on the gas and by the gas, so they're actually, positive work is not being done on the gas. That would be somebody pushing down on the thing. Positive work is being done by the gas, because for that statement, we're looking at it from the gas's perspective, which AP doesn't normally do. But for this part of this question, they're saying, if you were the gas, how would you describe the work you did? Well, if you're the gas, there you are, that's you right there, you would say, we did positive work, because we pushed in the direction that the piston moved. And you would be right. See, it's all a matter of perspective. AP in general says that would be negative work in this equation because it's energy out, which is understandable. But then they throw this question at you. Whew, this is the right answer. Positive is work. Now the good news is it's positive in either case. So if they'd have said negative was work done, all that, they could have really. But we got to go with this, because the work that is done by the gas. From the gas's perspective, it pushes and it moves. It pushes this way and the piston moves that way. So that's positive work. 27. Last one, I believe. So bastards. example of an ideal gas is initially at state A, shown in the graph, taken through the cycle. What is the net work done? Okay, so finally we get one of those questions. The net work done for the cycle is the area under. Now, this represents negative work according to AP. This would represent positive work. The negative work, because right, volume's increasing, that's negative work according to AP. So the area of these two blocks, which would be the area under this line, is negative. The area under this is technically positive. So when you subtract them, the negatives are bigger. So this net area should be negative. Well, good, they're all negative. So we just need the area of this guy. So that's going to be 1 unit across, a height of 1 unit. But then half of that, right? Because it's a triangle, so it's 1/2 base times height. So our 1/2, our base, is 1 times 10 to the negative second cubic meters, and our height is 1 times 10 to the 5th pascals. So it's 1 times 10 to 1,000. Cut in half is 500, so negative 500 according to this. Yeah, I would be correct. Checkamundo. All right, there's Thermo 1.